Good afternoon. Now I'll be presenting, now I'll be opposing magnetic trade. So here's a summary of the report. Firstly, the reporter investigated several relevant parameters such as turn density, the coil radius, as well as the chirality of the coil on parameters such as the velocity as well as the power of the trade. Furthermore, he also used different techniques such as the multiple Hall sensors as well as a camera to measure the velocity of the train through the coils. Furthermore, he gave what I feel is a rather complete theoretical account of the train's movement through the coil. He started with the Biot-Savart law to derive the driving force on the train, followed by the study of induction effects to examine the retarding forces on the train. Furthermore, he also empirically characterized many different parameters such as contact resistance as well as friction, which I feel is afterwards, he also compared the experiments with his theoretical account. So moving on to his strengths, I feel that first of all, his strengths include inclusion of many different effects into his model, such as the induction effects as well as the frictional force. This is rather commendable because it allows the reporter to gain it allows for a greater physical understanding of the phenomena, and furthermore, it also allows a greater predictive power of his model as he is able to account for all these factors. Furthermore, he also defined clearly the power as the energy of the can be used to power the train, which he also followed by experimental investigation. Furthermore, he also included a steady state theory and accounted for the acceleration in the train. And lastly, he investigated the special cases of curved coils, which I feel is rather commendable because this case of curved coils is not very easy to model, and it seems that he has been able to gain has been able to do this accurately. However, I feel that his weaknesses include not considering other effects such as magnetization of the battery, as well as accounting for the vibration of the train and the coil. And he also excluded some of the physical explanations of some of the phenomena that he may or may not have observed, such as the lack of rotation. Moving on to the discussion points. Firstly, I would like to invite the reporter out for discussion. Can you explain the physical significance of some of the parameters you varied?
Right, so I suppose what you mean by significance is how will it affect the train's speed and power?
Yes. I would like to discuss the effect of wire radius. So for wire radius, I would assume that firstly, changing the wire radius will affect the resistance of the wire. Am I right?
Yes. Actually, we did try to vary that in our experiments or so, but it is regrettable that we only have a few data points because we were not able to get that many wires. So here's a graph of our wire diameter, the effect of wire diameter on the speed of the train, terminal velocity. So as expected, as we increase the wire diameter, the resistance of the coil decreases, and therefore there's larger current and therefore larger driving force, which means larger speed. Yeah.
Okay, I'd like to thank the reporter for this clarification. Moving on, what about the number of magnets? So firstly, I understand that increasing the number of magnets will firstly change the mass, as well as secondly change the magnetic force. So can you explain some of the physical significance of these two effects?
Right, so intuitively, as we increase the number of magnets, the magnetic field strength will also increase. Right, you agree with that, right?
Yes.
Right, so with that, there will be increased driving force because the magnetic force on our train is now bigger. So this is why we see this increasing trend in the graph. But at the same time, because magnetic field strength of our train is now greater, there's an increased induction effect and therefore increased magnetic braking force. And since our weight of the train is also bigger, there's increased friction, which is why we see this decreasing trend.
Okay, I also like to note that this graph shows that you studied different coil diameters, firstly 33.7 and 22.6 millimeters.
Yes.
And I noticed that the peak of your graph has shifted to the right as you decrease the coil diameter. Why do you think this is so?
Right, so fundamentally this is a balance between two competing factors. The first factor is the increase in driving force, and the second factor is the increase in braking force. So if we were to draw the wire coils, let me use the whiteboard. Right, so if we were to draw the wire coils, we know that as we increase the coil diameter, the braking force, the driving force decreases because there's this increased distance between our magnet and the point of calculation.
I agree.
And also, separately, there's an increase in the area that we should consider for our braking force, the Faraday's law.
Yes.
Right, so we know that for this increase in area is proportional to the diameter of a wire squared or radius squared.
Yes, I agree.
But for the driving force, it is not a simple R-squared relation because our magnets are of finite size. So this difference in the fall off in these factors will result in a shift in the optimal points.
So to clarify what you say, the magnetic force will also fall off, and both the braking as well as the driving force will fall off. However, they fall off at different rates,
yes,
which results in this change.
Yes, that's right.
Okay. Do you think perhaps the other factors could have also caused this shifting? For example, contact resistance changing.
We actually tried to characterize contact resistance for different coils, and we find that they are largely the same. Because if we were to, and this is expected, because if we were to look at how contact resistance arises, it is because our magnet fundamentally is kind of straight at the bottom, but our coil is circular. So current has to flow in a constrained manner.
Yes. However, if you consider the cross section, for a wire coil coil diameter, you will expect that the area of contact will be slightly less than if the wire was much smaller, like the coil was much smaller.
Right.
I think this could have affected could have also resulted in the shift towards as you change the coil diameter.
Theoretically, this could be a possible concern, but we have tried to verify this, and we did not find any significant changes in contact resistance for different coil diameters.
Oh, okay, thank you. Okay, so I thank the reporter for this clarification. Now I'd like to move on to the next point. Firstly, the experimental technique. Can you go to the slide where you showed your setup, the one with the Hall probe arrays?
At the start of the slides. Near the slide. Yeah, here.
Okay, so these Hall probe arrays are to allow you to obtain the position of the magnet in your coil. Am I right?
Yeah, this is like a redundancy system. We have a camera and we have the sensors.
Oh, so it is for just to double check.
Yeah.
Okay. I think the reporter has done well in this part because having a redundancy system allows him to minimize things such as tracking errors, which will affect the camera but not the Hall probe arrays. Okay, so how do you fix the coil in your rail?
So below here, we have a sticky tape underneath our train, and we also sandwich our train between these two straight lines.
Do you fix down the middle part of your coil?
Yes, everything is stuck to this ruler, which is stuck to the table.
Oh, then can you go to slide 12, please? And play the video. Yes, I noticed that in the bottom video, there's quite a significant shaking of the coils as the train moves through. So, why do you think this is so? Because if you have stuck down your coils properly, I would not expect the coils to shake too much.
Yes, we do observe that there's some deformation in the coils as the train passes through. And we think this is because our tape that we use is not strong enough to overcome the driving force of the train.
Okay, in that case, I would suggest that you use a stronger tape to fix down the coils, because I feel that the shaking of the coils will affect quite a lot of, will significantly affect the velocity of the train, because this could firstly affect the contact resistance, secondly affect the friction, and thirdly it could also change the driving force on the train. So I feel that you should control this more clearly, more accurately.
Alright, but we still do see some good match between our experiments and our theories, so perhaps this is not a very significant factor.
Yes, however, if this is indeed a significant factor, seeing a good match between your theory and experiment, even though you did not control this, will indicate that the theory is wrong. Wouldn't you agree?
Yeah.
Yeah. So moving on to my next point, which is so you measure the contact resistance for the magnets, and you just left it there. Like you measure the voltage for the static case.
Voltage and contact resistance are two different things.
Okay, yeah, so you measure the contact resistance for the static case, for the magnets.
Yeah.
Okay, do you consider that there might be a possible velocity dependence on the contact resistance.
Yeah, I understand that there's some vibration of the train involved here, but I find it very difficult to visualize a setup where we can measure the resistance that the train passes through.
Firstly, I would like to clarify that even without the vibration of the coils, I feel that the contact resistance might also vary as the velocity changes. And secondly, I would like to make a suggestion to the reporter of how to measure the contact resistance. So he could have connected the ends of his coils to a CRO or some voltmeter and run the train through the coils. This will allow him to measure the voltage that is produced by the battery in the coils, which after measuring the internal resistance of the battery will allow him to calculate the contact resistance.
But the issue is that if you want to train through like that, there will be induced current in this coil, which will significantly affect voltage.
Yes, however, for a sufficiently long coil, which I see that you have, the induction effects on both sides of the coil should cancel out, and the voltage should give an accurate reading.
I disagree with that point. If we have induced currents in the coil flowing one way, then we know the potential at one side must be higher than the potential on the other side. And since there's no current flowing in the rest of the coil, this potential is constant over this non-current flowing zone. So there will still be a significant factor of induced currents.
I disagree because it doesn't matter what the induced current is, because the voltage that is induced in this region will be cancelled out by the voltage that is induced on the other side. So as a result, the voltage reading should be accurate. In any case, let's move on. How do you measure the magnetic field of your magnets?
We use hot probes, the same sensors we use for...
do you account for the magnetic field of the magnetization of the battery?
We can show that it's insignificant. If I come to just go through one final slide.
Okay, you have half a minute to finish it.
Right, sure, thank you very much. So what we did was that we tried to account, we know that for batteries there's a ferromagnetic casing around it, which we assume to be iron, which is a permeability of about 4,000 times that of vacuum. So we can see that even though magnetic field is distorted by the presence of the casing, the driving force and braking force is not significantly affected. So we don't think this is a great problem.
Okay, I'd like to commend my reporter for taking this into account.
Okay, thank you. The opponent now, you have 1 minute to summarize the discussion.
Okay, to summarize, the reporter has investigated many different parameters such as the turn density and coil radius, and investigated the effect of these parameters on the speed as well as the power of the train. He also used several redundancy techniques to measure the velocity of the train through the coil, as well as provided a rather comprehensive theoretical account using the Biot-Savart law, as well as taking into account induction effects, contact resistance, etc. He also empirically characterized many different parameters which he used in his model. And lastly, he compared his experimental experimental results with his theoretical predictions, and achieved a rather good fit. However, he failed to consider several different points, such as the vibration of the train, as well as sufficiently explaining the rotation. So in conclusion, I feel that he has done a pretty good job in answering the question.
Thank you. The reporter now, you have 1 minute to make your final remarks.
Right, so I feel that there are some points of concern over the battery magnetization, which I've shown just now that is insignificant. And there's also some points of concern over my measurement of the point resistance, the contact resistance as shown here. But I felt that the suggestion by the opponent would not really work very well, because there will be induced currents as I showed earlier, and then this will distort the measured contact resistance. And I think that my method of measuring it could negate this effect, and because it's a static case, and therefore offer more accurate results. And in conclusion, for report, I first went through a theory, and I'm able to account for various different parameters, key parameters such as the battery voltage, the coil radius, and number of magnets. And separately, I've also shown that I varied wire radius as well in the discussion. And I'm also able to generalize these to curved coils, which I feel this makes my theory more complete. And so I believe I fully answered this question. Thank you very much.